Hello everyone, welcome back. So today we will talk about a system with multiple qubits, all right? Because when you're doing computing, you just cannot confine yourself with one qubit. You have to work with multiple qubits, and how uh, these systems work is really necessary to understand, all right? So let's try to understand that. First, if you remember correctly, a single qubit, let's call this psi 1. Then a single qubit is a vector in a two-dimensional vector space, as you already know. And we can write it in a form something like this: alpha 0 plus beta 1. And you know that where alpha and beta are complex numbers. All right, so this is how you represent a vector space, qubit in a vector space. All right, so how you can get it physically, I think you already heard about it, that you can use the spin of an electron, or you can use the polarization states of photons, and there are many more examples. All right, so let's consider the example of the spin of electrons. So what happens if you have multiple electrons in your system and you want to work with it? You have already seen that there is a structure. Let's say you have two electrons. One of its states is psi 1, the other state is psi 2. So as you can see from your and this belongs to a vector space, let's say V, and this belongs to a vector space, say W. So the composite system will belong to this tensor product space. All right, and you already know about this tensor product and its structure. So let's try to work that out in details and try to understand what it means. All right, so let's try to understand the trivial example first. Let's try to understand the system with 2 qubits. So and then we can easily generalize to n qubits. So first, let's say that my psi 1 is equal to alpha 0 plus beta 1, and my psi 2 is equal to let's say gamma 0 plus delta 1. All right, how you can achieve such a system? Obviously what you can do is that you can take 2 electrons. Let's say this is a spinning electron. This is just a cartoon picture, and let's say this is another spinning electron, and they can interact. All right, so this has a spin up or down, this has a spin up or down, and then what you can see from here is that you can have the system in one of the 4 states, right? Where this can be up, this can be up, or this can be up and this can be down, and all the other ones. All right, down, up, and down, down. These are the 4 states. So how can you achieve that state? You can achieve that state by taking a tensor product. How? Let's take the tensor product of psi 1 tensor psi 2. Then how do you do that? That's pretty easy. You do like alpha gamma, and then you have 0 tensor 0 plus you have alpha delta 0 tensor 1 plus beta gamma, you have 1 tensor 0 plus you have beta delta, and you have this 1 cross 1. So as you can see, this is a superposition of 4 states. What are those states? One is 0 0, you can consider it like up up, 0 1, which is up down, 1 0, which is down up, and 1 1, you can consider it down down. All right. So what you can say is that your 2-electron system actually belongs to a 2 to the power 2-dimensional space, and we call it V cross, cross means tensor, sorry, it should be tensor V tensor W. All right, which is now a 2 to the power 2-dimensional space. So what will happen if you go to okay, now another thing is that this space V tensor W is not a space that only consists of vectors that can be written as direct tensor products. What I mean by that is that, let's say I take any vector psi that belongs to this tensor product space. All right. So now this tensor product space, I know that the basis elements, and I'll define a new notation now. Let's use a different color for that. From now on, rather than using this all the time, I will just write it as 0, 0. Okay, and so similarly I will write it as 0, 1. I'll write this as 1, 0, and I'll write this as 1, 1. All right, so whenever you see like multiple 1, 0, 1, this is nothing but a notation which is 1 tensor 0 tensor 1. Okay, this is the definition. We are using a new notation because we have to write it all the time from now. Okay, so let's say that I have a vector that belongs to this space. Now any vector in this space can be written in this basis. The basis for this space is the set of 0, 0, 0, 1, 1, 0, 1, 1. All right, so you can definitely choose a psi. Psi can be in one of these possible states. For example, 1 by square root of 2, 0, 0 plus 1 by square root of 2, 1, 1. Then what you can show is that this cannot be written as a direct product, a tensor product of two states. It cannot be written something like psi 1 tensor psi 2. You cannot do that. It is not possible. Okay, so this state is called an entangled state. So what you can see is that in this product space you have two kind of states. One is a product state, and and the other is the entangled states. All right. So now what happened? Now you can easily generalize it for arbitrary number of qubits. For example, you have n qubits. All right. Let's say you have psi 1, psi 2, up till psi n. So you have n qubits. Now if you have n qubits, okay, now if you have n qubits, then you can easily guess that your basis elements in the computational basis will be, and this will belong to the whole system will belong to this space, psi 1, psi 2 product up till psi n. All right, and now you can see the basis elements will be all the combinations in the computational basis. Okay, basis in the computational basis. Computational basis. So in the computational basis, you can write it something like this, where all of them are zeros. Then you start with, say, the first one is 1, and you keep on going. All right, and you end up with all of them are ones. This looks like the classical binary bits that you use, right? But that's not the case in quantum. We will see it in a minute. Okay, so first, what I'm trying to say, what is the dimension of this space? How can you guess that? The easiest way to guess that is that you have, in each basis element, you have like n boxes. right? So you can put either 0 or 1 in this box, similarly in this box, and in this, all the boxes, right? So you have two options here, you have two options here, you have two options here, you have two options here. So for n boxes, you will have 2 to the power n elements. All right, this is the same for classical bits. If you have n number of classical bits, you can encode n 2 to the power n numbers, 2 to the power n numbers with those bits, right? Similarly, your bases will have 2 to the power n elements. All right, so the dimension, so the punchline is that dimension of the space of n qubits is 2 to the power n. All right, and there is one more thing to notice. This is the one of the fundamental punchlines of quantum computing. That is, if you keep on increasing n, all right, if you keep on increasing n, your classically, if you keep on increasing the number of bits in your system, you will get your system will increase linearly, right? You can encode the number of information you can encode increases linearly. But what happens here in a quantum state, your basis elements, let's say this one, adds a new bit, new qubit, but your number of possible states, the total number of possible, the total number of possible states increase exponentially. And why this is happening? This is happening because you have entangled states. Because you see that you had these combinations before. If you add a new qubit, you can have either 0 or 1 here, right? So you will have two new possible product states. But when you write all the possible combinations, then the number rises exponentially. All right, so the conclusion is product states increases linearly. All right, but the whole system increases exponentially. By increases, I mean increases in size, increases in the number of elements exponentially. All right, so what does it imply? This implies that number of entangled states increases exponentially. All right, so this is the idea, and this is the power of quantum computing, that you have more, you can incorporate more information with these entangled states. So this gives you an exponential number of possible states. So you get your stored information can be increased exponentially by increasing number of qubits, and that is done by by using the entangled states. All right, and this was missing in classical computers, and that is why we have that drastic improvement in complexity. All right, we will talk about it in more details in the upcoming videos. Okay, thank you so much.